let's say you want to measure the position of B as a slider, right? So if you want to measure the position of B, you have to write B. So B will have some coordinates. In that vector, you have to write B. B you can also find with respect to the links like OA and AB. So in that form also you have to write it. Okay, so like A plus B minus A means vector A, which is A cos theta A sin theta, plus B minus A, which is B over here, and A sin theta means H cos theta S sin theta, and that's equal to this. And then you have to just make that derive with respect to time. You get this part. Okay, so this is just the derivation with respect to time. And because you know a few things over here, like phi, you know, and all those things, you know, so you can just solve it further. So for example, let's say you want to find theta dot. So phi dot, you don't know. So you will eliminate this phi dot and keep it everything in terms of theta dot and s dot. You will have this equation and you can find s dot from there. So like that you could have find the velocity or angular velocity, whatever we are asking with you, right? Angles measurements are okay, that you can do with that, no problem. Angles measurement were good. Okay, so with uh, geometrical methods, angles are okay, but angular velocities or velocities you could have find with this. Okay, anyway, so we already seen two examples. So let me just move to the current lecture. Is there anyone else who still wants to show this assignment number 2? Please raise your hand if you want it. Okay. See, assignment number 2 was very simple. And the only thing is that when you will draw the kinematics diagram of this assignment or this mechanisms, you will see actually it's a simple 4-bar linkage. It's a simple 4-bar linkage, and you just have to follow the same pattern that we have used in the 4-bar linkages in terms of the vector loop. Right? Very simple. You just have to make a fixed link, which has this link A over here. Let's say this is your B. And then it has a connection from here to here, like, let's say this is C. Okay. So you just have to give the link lengths. Okay. So in terms of vector, you have to solve it. And so if you are trying to solve this with in terms of the vector, how you can solve it. So let's say you want I'm asking you to determine the angular velocity of the crushing ram. Okay, so I'm asking you the angular velocity of the crushing ram. So okay, so yeah, so that I'm asking, and you just have to write the equation in terms of the B and A. Means you already know what is the position of B in terms of the vector, so that you can write because you know these link lengths, right? You can do it mirror twice, once from this direction and once from this direction. You will actually get the 4-bar mechanism which we used before to study the mechanisms. Like, so similar way you have to apply it here. So for B, what coordinates you will have B with respect to O? So that you have to write. Uh, so you will have uh, simple 4-bar mechanisms. So you just have to apply. So first you will see A plus B minus A, and then C plus B minus C. Correct? So location of A. So oh, 90 degrees over here. It's not a problem. So A plus B minus A is equal to C plus B minus C. And you just have to introduce the vectors of all the things. Okay. After putting the vectors, you just have to differentiate it once. And so with respect to theta or your angle, you can differentiate it. You have already been given the crank rotates at 120 RPM. So you can determine the velocity. So this angular velocity is actually already given because 120 RPM is already been given. So from this angular velocity, you can find the speed or velocity of A, and you know the velocity of A. So that from that velocity of A, uh, you just have to find the velocity of AB, and using A and the velocity of B means omega V, AB, you can find velocity of B very easily. Okay, so try it with once again with the vector loop method. Okay, uh, and I was expecting you to do that because we were doing everything in the vector loop only. So there was one more assignment that I was thinking to discuss with you with the same way, but you guys didn't do anything. So okay, so let's discuss this assignment. So here you have assignment number 4, and so you can see it's you have a conveyor or a plate which using the hydraulic ram you are using to lift it up, okay, at some angle. So uh, if we make a kinematic diagram of this uh, mechanisms, you will see it's something like this, right? So A and C, if you see it's here, this is A, this is your C, and this B, okay? So slider is actually your hydraulic ram, okay? So B is sliding over, it's not sliding, it's like just moving as a hydraulic ram, and this link 4 is connected to it. So input you are actually giving from here to move this slider B up and down, right? So simple. You can use mechanisms geometry. Okay. So using the mechanism geometry, because we don't know everything. We know that this part is 1, this part is 3, this part is 6. And to solve even it with vector loop, first you have to find AB. This angle 20 you already know. So this total angle will be 110, right? And using this triangle, you can find this angle, you can find this angle. If you know this angle, you will get to know what is the, what you say, this angle means the remaining angle. This part you can draw. Similarly, if you know this angle, and as it has already been given that it is something here as okay, so you can find this angle just by using solving it for geometry. You can find this angle, and you can also find this angle. So how you will find this angle? So basically, first you can, using this trigonometric function over here, you can find angle ACE. Okay, that is nothing but tan inverse 1 by 3, right? And similarly, you can find angle CAE, that is tan inverse 3 by 1, right? So from here you will get some uh, angles. So one will be approx, this will be approx 18 degree. That's not exactly 18 degree. It's approx 18 degree. And you will get this one. Okay, so from here, you find these two angles. And after this, we already know that what will be the, if you want to find out what is AB. Okay, because once you know AB, then only you can write any vector for B. Okay. So in terms of any theta or something, and theta will be this one, right? So AB, we can find it very easily like this. So we will take this triangle in which, because this is not totally perpendicular, so we can take AC square plus BC square, and we want to find means minus 2 AC to BC to cos angle this ACB, this angle. So because you know this angle, you already know this angle, because you just have to subtract 110 minus this 18. So approx 92 degrees you will get this angle. Actually it is 91.05 something you will get exactly. And you just enter this, you will find AB over here. AC and BC, uh, you know, because AC you can calculate from here using the trigonometric function. So 1 square plus 3 square under root, you will get this one, right? And yeah, so that's all. And then you just have to apply vector loop method over here to find it in terms of the theta. I will give you one more chance, and so some of you just volunteer and do it. So now instead of question number 1 and 3, I ask you to do assignment 2 and assignment 4 in terms of means you have to use vector loop method to find the velocities and whatever we are asking. Okay, so rate that conveyor belt is being lifted, and here we are asking determine the angular velocity of the crushing ram. Assignment 3 and assignment 2, you can try. Assignment 1 you can try once again. So we have asked angular velocity of the lower link and velocity of the B with respect to point A. So you just have to write once again in the vector loop. And so Latifa, we can just move it to next lecture to show them.
Yes. Move on. So there's still one more chance for
Yeah.
next meeting, right? For the students to answer by using the vector loop.
Yes, because for assignment 1 and 3, their answers are correct, but they didn't try it with vector loop because with vector loop, it will be more easy to program it. So let's say if you are using MATLAB or some C codes or something, it will be easy for you to program it and find anything, because there if you are writing codes in trigonometric functions and in these many long codes, it will be very difficult, right? And if you know the equation, you just have to enter whatever changes in angle, length, whatever is happening over there, you just have to change the parameter and you can find the values very easily. So we are just preparing you for the purpose when you will program or code something for the mechanism, some things like this, right? So use the vector loop method and then try it. So this mechanisms is also very simple. It's like uh, this is a slider crank mechanism. So you can see how in the examples in the lecture slide 3 how we did it, and then you can try it. So Ladiva, do I have to share the presentations for lecture 2 and lecture 3 with them?
Yes, why not?
Okay, so I will share those presentations, and from there you can take it out, means how uh, we have solved it over there, right? Okay, so let's move to our new topic, that is instantaneous center of uh, velocity. Okay, so what do you mean by instantaneous center of velocity? It's, we have seen this, what you say, is all the uh, problems related to, or is we have solved it for kinematic mechanisms. We draw the kinematics diagram till now. We see how position and displacement can be determined. We have seen how you can use the vector loop methods to find the velocities and angular velocities. Okay, so now we will talk about instantaneous center of rotation, and or you can say instantaneous center of velocity. So these this terms is actually defined uh, means point of rotation for any link. So in generally what happens, the motion of any link in a mechanism is neither purely translational nor purely rotational. Okay, so any link, it's about a point, it is rotating, having some rotation, right? Or having some translation. So it's not purely translational, not purely rotational. And but the whole link at any instance, okay, so a whole link at any instance can be assumed to be in perfect rotation with respect to a point known as instantaneous center of rotation, and that is also known as virtual center. Okay, so yeah, so here you can see that at any point on a rigid body, or here you are seeing that this is your rigid body, and any point on a rigid body or on its extension that has a zero velocity. Okay, so anywhere that has a zero velocity, so that we can write it as V is equal to omega into Ra by ICB. Okay, this. So this velocity at ICV that you will see, it will be zero. And with respect to ICB, your body will be having some velocity. Okay, and that is VA. Okay, in other words, if I say, let's say you have one link. Let's say this is your link A, B. Okay, and so if this link is rotating, so what will be happening? You will have one axis on which you will have a point. And with respect to that point, your link will be rotating. So let's say now your link is here, and after some time, it reaches somewhere here. So here your location of link AB. Okay. So it is making this path. Okay. And this link is rotating about one, which is called as this I, and this is your instantaneous center of rotation. Let's say at any point on this link, you want to find the velocity, or so when you're finding the velocity, that any point on that link, that's also rotating with respect to that center, means instantaneous center of velocity, and that's will be passing from here. It will be also making the same path, right? So at time t, let's say you are here, and at time t plus delta t, you will be here. So for moving from here to here, this link is always be rotating about this instantaneous center of velocity. Okay. So for any point on this link, if you say omega AB, if you want to find the if you know the angular velocity of omega AB, then you can find the velocity of let's say B you want to find. Then you should know BI. What is the distance of BI? You can find. Then if you want to find BA, you should know AI. And if you want to find BC, you should know CI. Let's say this is C. Okay. So just for example, I'm explaining what the definition of instantaneous velocity means. So the whole link you're seeing here at any instance can be assumed to be in perfect rotation with respect to a point, that is your I, also known as instantaneous center of rotation. At some places you will see that we are also called it as virtual center. Okay. So actually you're not seeing that center, but it's a virtual center along which it is rotating. So how that virtual center looks and from means why you are not seeing it on the exact link. Sometimes you will see it on the at the joints, but many times you will see that it is not at the joint, it is some the extension. Okay. So the locus of this instantaneous center of rotation for a link during its whole motion is actually uh, is known as the centroid of the link. Okay, so the locus of this uh, instantaneous center of rotation for a link during its motion, we will also call it as centroid of the link. Okay, so locus of axis of rotation is also known as xoid of the link. In some places you will see. So for example, if I have given you the velocity of A for a point A on a rigid body and the angular velocity, then the ICV is located perpendicular from the VA. Okay. And so the same thing that I was telling you, omega, you can move it here, and this RA ICB means this distance, you just have to enter. So what is this RA ICB? If you know the velocity, if you know the angular velocity, you can find it. Okay. Now, if you have 2 points, okay, from the same body and they are rotating, so you will have instantaneous center of rotation along which its whole body is rotating. And for each point, it will be passing from the same instantaneous center of velocity. Okay, so line intersects at one point, and from there you can find BA and BB. Okay, so what will be VA and what will be BB? So VA will be simple. You should know, let's say this whole body is rotated by angular velocity omega. So if you know uh, means what omega is, you just have to multiply it with A. means distance of this RA from instantaneous center of velocity. Okay. Similarly, VB omega into R A means RB, sorry, from instantaneous center of velocity. Okay. So very simply you can find it. Now, if you have a case where means parallel lines are intersecting at infinity, means this body is there, but it is not rotating, it's sliding. And one example for this we can consider like, let's say you have a plane and on that you have a block. Okay. And this block is going in this direction. Okay. And here you have 2 points A and B. Okay. So from the direction of the motion, you will always have this axis passing at the perpendicular. Okay. Like here you have seen the direction of motion was this, and the axis which will pass from the instantaneous center of velocity will be perpendicular to the velocity direction. And wherever they will meet, you will get instantaneous center of velocity. But in this case, this is the direction of motion, and when you will plot it, these lines will never meet. Okay. Or we can say in other words that they will meet at infinity. And what that infinity is, we don't know. Okay. So we call this at instantaneous center of velocity. You will have at infinity, and omega you will consider here as 0 because you do not have any angular rotation over here. Okay. And velocity of A and velocity of B will be equal. Okay. So that instantaneous center of velocity at infinity, it actually means this thing. Okay. And it's quite intuitive and it's quite obvious that you will have this. Two more. Yeah. So now one more thing we will see that two lines fall on top of each other. Okay. So let's say you have point A, point B, and both the velocity direction are in the same direction, but this body is actually rotating. Okay. So whatever is the velocity of A, instantaneous center of its axis will be passing from ICV, and B is also actually on the same axis, and the direction is also the same, so it's passing from the same axis. But how you will find the ICB? Simply you just have to consider any other point with some direction, plot it, and wherever it is meeting in this axis, you will get the ICB. Okay, so this is how you can find where is the instantaneous center of velocity, right? I will give you a few examples. For example, turning pair. Okay. So in turning pair, what you will have, let's say you have one link, that is your link 1, and here you have your joint, and from this joint your link 2 is connected. So what will be the instantaneous center for these two links is where their centers will meet. So it's actually will meet here at the joint, and that will be I12 we can write. Okay, so this is actually your instantaneous center, ICV. Now, similarly, let's say you have a flat plane, but instead of sliding, now you have a roller over here. Okay, you have a roller, and it is rotating with some angular velocity omega. Where will be the instantaneous center of velocity for this pair? Any idea? It is going in this direction, so velocity of rotation is here. See, for this kind of pair, as I told you, you have to just draw velocity with respect to perpendicular to velocity of direction of your velocity. So you just make perpendicular over here. So your instantaneous center will always be over here at the contact point of your roller and the flat plane on which it is rolling. Okay. So one link is fixed link on which it is rolling, which is another link. That's your roller. Okay. Uh, Other way to find it is like, for example, let's say you have this roller, this thing. Let's say you don't know what is VC, okay, direction of VC. So simply what you will do, let's say you consider 1 point over here, 1 point over here. Okay, it is rolling on this direction, means this flat surface. Obviously, velocity of this roller in this direction, but we are not assuming for now this VC. Okay, so let's say you have this point. So on this point, this direction will be here when it is rolling. Similarly, for here, the direction will be here. Okay, or let's say you have a point over here which will have a direction over here. But it is because it is going in this direction, you will have this VC like here, and this is your radial velocity. Let's say VR. This is your VC. Similarly, here you will have your VC, and uh, here you will have your what you say radial velocity omega. So you just have to extend these lines where you are forming these. So it's not actually here. You will have this thing in this direction, and they will meet over here. So that will be your instantaneous center of velocity at I12. But this is quite simple to understand, and just follow this for roller part, right? Okay, now a velocity of a point with ICB. So consider a 2 point A and B, okay, on a rigid link. So let A and means velocity of A and velocity of B be the velocities of point A and B at a given instance. Okay. Other parameters are given like alpha and other angles has been given. So if VA is known, if you know the velocity of A in magnitude, okay, and direction is also known, and BB direction is only you know. Means for BB you only know the direction. Then the magnitude of BB may be determined by the instantaneous center method also. Okay. So how you will do that? So first you have to draw AI and BI perpendicular to both BA and BB. So where is your BA? This one. And BB is this one. So you just have to make perpendicular to it from here and from there. And wherever they are meeting, it is I. So these lines intersect at I, which is known as instantaneous center or virtual center of the link. Okay. Okay. And the complete rigid links rotate about the center I at a given instance. Okay. So whatever instance you will take, that complete link will be rotating at about the center I. So the relation that we are showing you here may be used to determine the magnitude of the velocity of B. Okay. So VA we already know, means if you know VI plus omega k into R AI. Okay. So omega into k into R AI. And so in the k direction, and these vectors we will take from A to I. And similarly, means VA you will get as omega is equal to VA divided by RAI. So that we already discussed. Similarly, VB, we can write it as omega into RBI. Okay. So this I have already told you. So when two links are connected by a pinpoint, The instantaneous center lies on the center of the pin, means at the joint. So such an instant center is a permanent nature. It doesn't change even if the link moves. And if one of the fixed link is fixed, the instantaneous center will be fixed on the fixed type link. Okay. Um, Now next thing, when two links have a pure rolling contact again, so without slipping, the instantaneous center lies on these points of contact. So that I had explained you, like for example, A and B, two other points are there. You just have to consider the velocity. Make perpendicular from here. You will always find it over there at the contact of roller and the fixed plane. Okay. So at this point, the velocity will have the same velocity on both the links. Actually, you will have. Okay. So you have another example over here. So when two links have a sliding contact, okay, so here you have a slider and the instantaneous center lies at the center of curvature. Okay, so for example, let's say you have this curvature, so your instantaneous center will lie at the center of curvature. You just have to consider 2 points over there, draw the velocity, make perpendicular to it, and wherever your instantaneous center is meeting, that's your center of your actually curvature also, along which it is moving. So it's the instantaneous center lies at the center of curvature of the path of contact. Okay, so this point lies at the common normal at the point of contact actually. Okay, uh, this we have already discussed, VA and BB. Here when we will draw the perpendicular, you will find the instantaneous center at infinity. Okay, so it will be at infinity. And one more thing, let's say you do not have curvature like this. Let's say you have something like this. And your roller is here, means your slider. So here again, you have to just consider 2 points, A and B. Let's say it is in this direction and this is in this direction. You just have to draw it, the perpendicular from the velocity directions, and you will get I12. So that is your radius of curvature actually. This radius. So this is your center of curvature and this is your instantaneous center. Okay. So when I'm writing 1, 2, so actually your link 1 is this fixed link and link 2 is this. Okay. Okay. Now let's see how you can determine the instantaneous center of velocity for 4-bar mechanism, ICV of 4-bar mechanism. So whether it is the 4-bar mechanisms or uh, it is a 5-bar mechanism, 6-bar mechanism, 7-bar mechanisms. Whenever you will get this kind of questions in which you will have multiple linkages, what you have to do is just draw a circle. Okay, and in that circle, make equilateral diagram for all the links and point me those dots as the 1, 2, 3, 4. So what these 1, 2, 3, 4 are representing? These are representing the links. Okay, so here you have your link 1, link 2, link 3, link 4. Okay, so this is your 4-bar mechanism. So for link 1 and link 2, ICB will be here, I12. Similarly, link 1 and link 4, ICB is here, I14. For 2 and 3, it's I23, and for 3 and 4, it's I34. Right? So this you have drawn. So what it is showing, that link 1 and 4 is in connection. Link 4 and 3 is in connection. Link 3 and 2 is in connection. And link 2 and 1 is in connection. So it's showing that instantaneous ICVs are actually already there in their connection. Now, if you want to find out, okay, I want to find how link 3 will rotate with respect to link 1. Okay, how link 3 is rotating with respect to 1 means basically I want to find how link 3 with respect to 1 is rotating. So you just have to extend the opposite links from means side links from the link 1. So this is your link 2 and link 4. You just have to extend them like this, and you will get one point where they will contact, and that's I13. So this is the instantaneous center or ICV for I13. So here you will make a line between them. Similarly, I24 also you can find. You just have to miss. Is there a possibility to make this connection? Yes, there is a possibility to make this connection. So obviously you will get I24 as well. So like this, you will make this I24. How you will get that? So between 2 and 4, you want to find opposite links, whatever from there it is. You just have to extend them from the 4 like this and this. So here you are getting I23, here you are getting I13. This is I24. You just have to extend these link lengths, and wherever they will meet, that's your ICB. Okay. Okay, so now when you will complete this circle, you made all the connections. It means now you already got all the ICVs or all the possible ICVs that your mechanisms can have. Okay. Uh, Now there is one term called as centroids. So you are seeing that link 3 over here. This is your connecting link 3. So link 3 moves, the ICV will also change. Okay, so as your link 3 is moving, your ICV will change. So let's say previously it was when if you extend it. So let's say previously it was here. Then your link 2 moved. So let's say the ICV again changed over here and it reached here. So this I13, whatever curve it will make for this means where you can find this ICB. So this is the locus of all ICBs. That's called as centroids. Okay. So you're just finding the locus of all the ICBs, and that is called as centroid. So what is the locus of all the ICBs? That will be called as centroids. Now let's find out the ICB of slider crank mechanism. So it's very simple. You have this mechanism. Here you have fixed part. Here you have fixed link. This is your link 1, link 2, link 3, and link 4 is your slider. Okay. You have drawn it here. Link 2 and 3 have connection. Link 3 and 4 have connection. Link 4 and 1 have connection. So link 4 and 1. So this is also actually link 1 as a fixed. This is 1. And link 1 and 2 obviously have connection. I 1, 2. Right. Now, what are the possibility that you can make over here? So this and this, right? So first see this one. Let's join it, I13. So opposite link 2 and link 4, you just have to extend. So what is the opposite points from this link 2 and link 4? You just have to extend it. You will get I13 over here, right? Similarly, let's see, this 2 and 4 can have a combination for ICB. Okay, I just join it. So 1 and 3 you have to extend. So from what do you say, 3 you are extending like this. Okay, and so 4 will be forming over here. So uh, once it reached here, you just have to extend a line from here anywhere. So it will be moving because it's a slider, so this 2 4 will be changing most of the times, and you will get this I24. Okay. Okay. Uh, Now the velocity analysis of ICBs, how you can find the velocities from the ICB. So, so let's say I13, okay, and you know omega 2. Okay, so let's say you know that it is moved by angle theta 2, and you know omega 2 from there. Okay, so omega 2 is known. So the magnitude of the velocity of point A, magnitude of the velocity of point A, that uh, can be computed. So you can compute it very easily. So because you know omega 2, so omega 2 into O2A. O2A is what? This is A. This is your O2, let's say. Okay. So this distance, because uh, your center of instantaneous centers are over here and here. Okay. So VA you can find. Then its direction and sense can be determined by fraction. So note that point A is also instant center, but and it has the same velocity as the part of the link 2 and part of the link 3. Okay. So at this point particularly you will have the same velocity which is sharing by link 2 and link 3 as well. So since the link 3 is effectively pivoting about I13, okay, at this instance, and the angular velocity omega 3 can be found because we already know VA. So how omega 3 can be found? So omega 3 is this. Okay. So omega, this link 3 is through this ICB. So omega 3 is equal to VA, and A you have to find I A to I. This I distance from A to I13. This distance. Okay. So if you do that, you can find omega 3. Similarly, you can find omega B, because now you know omega 3 from here. So omega for this particular link will be same, even though the velocities of A, B and C can be different. Okay. So BV we can find omega 3 into A means omega 3. It's not A, it will be B I3, means B to I13, this distance. This is wrong. B to I13. You can find omega 3 means BV. And similarly, you can find VC. You just have to find this to I13. Okay. Now, once BV is known, omega 4 can also be found. This omega 4. Because you know the velocity of B, and BO4 is this. This is your O4 actually. So you know that this is 4. So BB divided by this link length, and you can find omega 4. Okay. So finally, VC can also be found. The same thing. VC, omega 3, you already know, and C, I3, distance from C to I13. Okay. So VC, or the velocity of any point on the coupler, can be found from this, is like this. Okay. Now we have this Freudenstein's theorem, and here you are seeing that line connecting I13 and I24 is called collineation axis. Okay, so line connecting I13 and I24. So where is I13? This is I13 and this is I24. These are the collineation axis. And from here, what you can find, so this is actually like link 3 is moving about this center, and link uh, 2 and link 4 are moving, rotating about these two, this center. Okay, so here angular velocity ratio you can find. So here you have omega 4 by omega 2. So these two links you can consider, and because it is at the same uh, same same instantaneous center of velocity, we can write it as I12 I12 to I14 I24 I12 to I24 and I14 I14 to I24, this distance. So if you just divide it by that, you can get very easily omega 4 and omega 2. Okay, because it's very easy to find this, because it's on this line extension of I12 and I14. It's on the fixed plane, and this distance is easy to find as compared to this one. Okay, so if you want to find the omega 2 and omega 4, so like that you can find out. Okay, and the axis on which it is lying, it is collineation axis. Right, so that's Freudenstein's theorem, and so that's all for today. If you have any question or any doubt, you can ask. So we'll take what do you say, 10 minutes for that.
Sir, can I ask a question?
Yeah.
What's the difference between the center of velocity and center of rotation?
So difference between center of velocity and center of rotation you are asking. Okay.
Yeah.
Your velocity means whatever your link is, means whatever your point is, let's say it has some direction. Okay, and your link is rotating, let's say that point is on that link, so your link will be rotating about some center, means some point, or you can say that about rotating about that point, and about that point only you have that velocity. So that's instantaneous center of rotation. Okay, so we call it a center of rotation, and you can also call it a center of velocity, because about that center your velocity is having the direction while rotating. That's why when you had this when I show you this example in which you had this flat surface and you had this point A and B over here, and it is going in this direction, so point A and B's direction is same, and it made a perpendicular. Okay, so what will be the center of rotation for this? Actually we are assuming that all the bodies which having the velocity or which are moving, we are assuming that they are rotating, but actually this is translating, it is going in some other direction. So in any way it is not rotating. That's why we are calling it that ICV for this means instantaneous center of velocity, or this ICV we can also call it as instantaneous center of rotation. It's at infinity. While for other links like this, if you see I13, I24, these are actually instantaneous center of velocity, and you can also call it as center of rotation. for any link. So this is the center of rotation for this link. Means means for this link. So about this link, you have this center of rotation. Similarly, you have center of rotation for uh, this and this link. So whatever point you consider on this link, it will also have the rotation from there only. Okay, so it's quite normal. So if I explain in general terms, like in general, the motion of any link in a mechanism is neither purely translational nor purely rotational. It's a combination of both. Okay, but what we do, the whole link at any instant can be assumed to be in perfect rotation. We assume that it is in perfect rotation. That's why getting this infinite swell or center of velocity. Otherwise, obviously they will never meet. That we know. That's why we are writing infinite for this case. Okay, and that point we call it as instantaneous center of rotation or virtual center or instantaneous center of velocity. Okay, and this locus of instantaneous center of rotation for a link during its whole motion, we call it as centroid. So centroid we have already seen. There was centroid, yes, here. So the locus of instantaneous center of rotation for a link during its whole motion is known as centroid of that link. Okay, and locus of instantaneous axis of rotation is known as xoid of the link. Okay. Okay, so any other question? Is there any other question you would like to ask? Okay, what I will do, I will just cover one more part over here. So we have seen this Friedland's theorem, and there is one more theorem. So Latifa, are we going to cover Kennedy's theorem as well?
Which theorem?
Kennedy's.
If you would like to, you can cover it.
Okay. So let me just add one slide. So similar to this Friedland's theorem, but there is one more theorem, that's Kennedy's theorem, and I will just explain it to you. Okay. So what this theorem says, for the relative motion in a mechanism, for a relative motion in a mechanism related to any link. So let's say you have 4-bar links. So motion of this link with respect to this, motion of this link with respect to this, motion of this link with respect to this. So any relative motion. So for all the relative motion in the mechanism, the 3 instantaneous centers for any 3 links should lie in the same straight line. Okay. So what it says, for the relative motion in a mechanism, the 3 instantaneous centers, you call it a center of velocity or center of rotation, it's up to you, for any three links should lie in a straight line. Okay. So this is the Kennedy's theorem, and if you see the Fluent's theorem also, so here what you are seeing, this is the Miss I24, what it actually represents. So it represents ICB for link 2 and link 4. Similarly, I13, what it represents? It represents link, ICB for 1 and 3. Okay, and where they are lying? They are lying on the same line. And here in Fluent's theorem, it's collineation axis. Similarly, in Kennedy's theorem, you will have the same thing. And from there, you actually get the theorem of angular velocities. Okay, so it just simply says, let's say you have link, this is your link M, and this is your link N. Okay, so what will be their ICB? It's a joint, it's IM N. Okay, so velocity at IMN will be is equal to, we can write it as omega m into IMN. So let's say it's here I1m, or it is I1n. Okay, so I'm just considering these 2 points as other instantaneous centers with some other links maybe connecting. So here I can write I1m, and this will be equal to omega n IMN I1n. Okay, so velocities at IMN. So what it will be? You can get either from this link or from this link, and this is how you can get it. So you just have to equate them and you will get this. So this is what theorem of angular velocity says, and it's very simple that we have seen till now. And just for example, we will take one example over here. So let's say you have this fixed link 1, this is your link 2, this is your link 3, this is your link 4. Okay, and this link 2 is we are giving the input, and it will rotate by angle theta. Okay, so now let's say my question is, if theta rotates by 180 degree, or we can say pi, means not by at 180 degree, rotate to 180 degree. Let me just rephrase it. Rotate to, it means theta will be is equal to 180 degree total. So what will be instantaneous centers? How you will find it? Where will be the instantaneous center? So very simple. You just have to make a circle, make 1, 2, 3, 4 on it. Okay, so link 1, 2, 3, 4 all are in connection. That you know, this connection we already know. Okay, now if theta rotates by 180 degree, how your mechanisms will look? So it will look something like this. So this is your, let's say, point along which your theta is rotating. It is rotated by 180 degree, it reaches over here. This is your link 2, this was your link 1, and here is your link 3, and here is your link 4. So like this your mechanism will look like. Okay, so for 1, 2, you will have I12 over here. This is your I13, sorry, 2, 3. This is your I34. Here you have your I41 or 1 3, whatever you want, you can write it. Okay. Now we have determined almost all the instantaneous. So we know 1 2, 2 3, 3 4, and I 4 1. So what will be I 2 4? I 2 4 I'm asking. So this is your link 2 and this is your link 4. This is a possible instantaneous center of velocity or instantaneous center of rotation. So what is I 2 4? Where we can find it? So normally what we have to do? We have to extend the opposite links from means which are connecting 2 and 4. Okay. So 3 and 1 you have to extend, and where they are meeting? They are meeting at the same place where you have I 1 3. So here at the same location you will also have I 2 4. Similarly for I 1 3, sorry, I 1 3, you will have it over here. This is your I 1 3. This is your I 1 4. Why? Because 1 you will extend and 4 you will extend for I 1 3. Means, sorry, 2 you will extend. So when you are extending 2, it's extending like this. And it is coming over here. And when you are extending 4, it is meeting here. So that's why you are getting I 1 3 like this. So it's at the same location of I 2 4 and I 1 3 you are getting at I 1 3 and I 1 4. Right? Okay, now let's say one more thing is given, that omega 2 is equal to, let's say 2 radian per second is given. Omega 2 is given. This omega 2. So I want to know what is omega 3. This is what I want to know. This is my question. So we will just use this formula. So what is omega 2? That is 2. Then I mn into I 1m. Okay. So from where it is making? So let's say it is A. And this link and this link, fixed link, distance between here to here, it is A. So this is also A. So from here to here, what is the distance? That is A. Okay. And omega 3, so when I'm saying omega 3, so you have to consider distance between, means you have to take this link so actually it is coming out from I 2 3 to I 1 2. Okay. So I 2 3 to I 1 2. So I 1 2 is here and I 2 3 is here. This is your I 2 3. Okay. So that's A. Now for omega 3 into, what is this part? This is your I 2 3 to I 1 3. This part. Okay. So I 2 3 is here and I 1 3 is here. So that distance is total 2A. So A and A will cancel out, and omega 3 you will get it as 1. Okay. So like that you can solve many numericals for finding these. If you have many mechanisms, you can find the instantaneous center of velocity. You just have to connect the links, find the velocity, connect the link, find the velocity, angular velocity, and you can find it easily, right? So that's all for today. If you have any doubt till now, please ask it, or else we will stop it here. And in next lecture, we will see again those assignments with what you say with vector loop function. So now I had added one more assignment, that is assignment number 4, this one. Okay, so for this you have to means you have to solve it whatever has been asked in vector loop form. Okay, so that's all for today. I will upload slides for lecture 2, 3 and 4, and that will that you can obviously follow if you want to it. Yeah, so that's all. So Latifa, any comment or anything?
That's fine for me.
Okay. Okay, so see you guys. Thank you everyone for attending, and I hope you will have nice